Hello everyone, myself Dr. Goutamiitm, Assistant Professor in Mathematics, Malda College, Malda. In this video lecture, we are going to study the concept of relation. And in this topic, I will explain the following 5 points, namely definition of a relation, some examples of relation, types of relation, equivalence relation, and fallacy. Okay, now let us start. Suppose A and B be two non-empty sets. Intuitively, a relation from A to B is a rule of correspondence that assigns some or each element of A to some or each elements of. So this is the intuitive definition of a relation from A to B. Okay. What it says is that suppose this is my set A, this is my set B. So a relation from A to B, we are defining a relation from A to B. We name the relation, say suppose rho. So this is a relation. We say that rho is a relation if there are some elements. Suppose these are the elements of A, these are the elements of B. Okay. So if suppose this element is associated with this element under this rule, this element is associated under this element under associated to this element under this, similarly this. So this is an example of a relation from A to B. So it may happen that an element of A is related to more than one element in B. It may also happen that there may be some element which is not related to any element of B under this relation. For example, you see this element of A is related to 3 elements of B, whereas this point or this element is not related to any element of B under this relation. So both the cases may happen in a relation. So this is the intuitive definition of a relation. Okay, let us give the mathematical definition of a relation. Suppose A and B be two non-empty sets. A relation, say rho, defined from A to B is nothing but a subset of A cross B. A cross B means the Cartesian product of A and B. So this this is the mathematical definition of a relation from a set A to a set B. What it says that, suppose this is my A, this is my B. Suppose we have three elements in A, we name it A1, A2, A3. Suppose here we have, suppose say four elements, B1, B2, B3, B4. Take the cross product of these two sets, A and B. Then we get the set A cross B. And the elements of A cross B, how many elements we have in A cross B? There are 12 elements. How? Because the order of A is nothing but the number of elements in A is 3. Order of B is nothing but 4. So order of A cross B, number of elements of A cross B is equal to 3 into 4, namely 12. So we have here 12 elements. Okay, we have 12 elements, and each element will be of the form, each element of 12 elements will be of the form x comma y, where x belongs to A and y belongs to B. Okay. Then the definition says that you take any subset of this set. For example, if I take this set as a subset of A cross B, then this is a relation. So this is a relation of defined from A to B. So what it says that any subset of the set A cross B will be a relation from A to B. This is the mathematical definition of a relation. Now, already we know that the number of elements of A cross B is 12, right? So how many subsets we can get from this set? The number of subsets, the set of all subsets of A cross B is known as power set of A cross B, and the power set of and the number of elements of that power set will be 2 to the power 12. So we can get 2 to the power 12 number of subsets of A cross B. So how many relation from this definition? How many relation we can get from A to B? And the number is 2 to the power 12. Okay. So this is the mathematical definition of a relation. Okay. Now we all are familiar with the relation, with the word relation, right? From our childhood. Say, for example, suppose you have a relation with your father, right? You have a relation with your mother also. You have a relation with your, say, grandfather also. You have a relation with your friend, right? So I have listed here only 4 relations. So there are many relations, we are familiar with them in the real life situation. Okay, and all the relations I have listed here are distinct. So question is, these relations, can we describe all these relations in the language of mathematics? Can we describe all these relations in the language of mathematics? Okay, and the answer is yes, we can. Say, let us try to describe only this relation mathematically. So this is our mathematical definition. of a relation. So to describe this relation, we need two non-empty sets, namely A and B. So we have to first choose two non-empty sets A and B to describe this relation. So let us suppose A, the set A is the set of all fathers of your family. B, the set of all sons of your family. Okay, we are defining these two sets from your family. A is the set of all fathers of your family. B is the set of all sons of your family. Okay. Suppose the elements of A starts from your grandfather, GF. GF means grandfather. Then your father will come here. Say suppose your uncle will come here. You have, say, elder brother. So these are all members of this set. B, suppose, so elements of B will be father, then uncle, then you, then your elder brother, and then suppose this notation stands for uncle's son. So these are the elements of the set B. So we have got two sets A and B. Now we are going to describe this relation in this way. Okay. Now let us define a relation. Say row from A to B in the following way. What is that? For X belongs to A, Y belongs to B, X has a relation. X has a relation row with Y denoted by X row Y or its equivalent form X comma Y belongs to row. So X has a relation row with Y denoted by X row Y or its equivalent notation is X comma Y belongs to row if, I should remove this one because the lack of space. If and only if, or if you say if X is a father of Y. So we are defining a relation row from A to B in the following way. X is row related to Y if and only if X is a father of Y. Okay. So let us check the elements of row. So we can easily see that GF is related to F, right? Because grandfather is a father of father. GF is related to your uncle. Okay? F is related to you, right? F is related to your elder brother. U is related to your uncle's son. Okay, so its equivalent notation is GF comma F belongs to row. This one GF comma U belongs to row. This one F comma U belongs to row. This one F comma AB, and this one U comma US belongs to row. So these are the only elements of the set row. So row becomes GF comma F, GF comma U, F comma U, F comma AB, U comma US. So this is our row. Now take the cross product of A and B. So there are, here is the number of element 4, here is the number of element 5. So total number of elements in A cross B will be 20. Okay, and the elements will be of the form, say GF comma F, GF comma U, GF comma U, GF comma EB, GF comma US, dot dot dot. We are getting 5 elements for this element. Similarly, we will also get 5 elements for this element. Here for 5 elements, here also 5 elements. So I am not listing all these elements. So this is our A cross B, and it is clear that this set row is a subset of A cross B. So clearly, row is a subset of A cross B. So row is a subset of A cross B. So whatever be the relation may be, we are familiar with them in real life situations. All these relations can be described mathematically in this way. So this is the concept of relation. Okay. I think you have understood all these things. Next, give some other definition. Suppose say A is equal to A comma B comma, there are 3 elements, namely A, B, C. Then if we take this as a subset, okay, let me tell you one thing before that. Here the definition of relation is row is a relation from A to B, right? If row is a subset of A cross B. In particular, if A is equal to B, then row will be a relation from A to A, okay, and row will be a subset of A cross A. So instead of saying row is a relation from A to A, in this case we'll say that row is a relation on A. Okay, what I'm saying is that if A is equal to B, then instead of saying that row is a relation from A to B, A to A, we call it row is a relation on A. Okay, now take an example. Suppose A is equal to this. We are going to define a relation on a set, on this set A. Suppose row is equal to say A comma B, B comma C. So it is clear that this is a subset of A cross A. Is trivial. So rho is a relation on set. We can get lots of examples like this. Okay. Now let us come to another point for types of relation. Types of relation. Let me tell you one thing. Suppose rho is a relation from A to B. Okay. Suppose X belongs to A, Y belongs to B. If X is rho related to Y, then we denote it by X rho Y, or its equivalent notation X comma Y belongs to B. If there is no rho relation between X and Y, then we denote it by this symbol, or we denote it by this symbol. Okay. Okay. Now come to the next point, types of relation. Types of relation. Suppose rho is a relation defined on a non-empty set. Then the number one is rho is said to be reflexive if A rho A holds for all A belongs to A. That means A comma A belongs to rho for all A belongs to. If this happens, then we say that rho is a reflexive relation. Now come to symmetric relation. Whenever A rho B holds, if B rho A also holds, then we say that rho is symmetric. Okay. Next one. Rho is called transitive if whenever A rho B, there is a relation between A and B, there is a relation between B and C. If or implies A rho C, then rho is called, we have already written this. So rho is called transitive if whenever there is a relation between A and B, there is a rho relation between B and C, then that implies that there is a relation between A and C, then we say that rho is transitive. Okay. Okay. Now, if rho is reflexive, symmetric, and transitive, then we say that rho is an equivalence relation. On A. So this is a definition of Now let us give some examples of an equivalence relation. Let us give some examples of an equivalence relation. Okay. Number 1. Suppose our set is Z, the set of all integers. We define a relation. We define a relation rho on Z by A rho B if and only if A minus B belongs to, A minus B is divisible by, say, 5, where A comma B belongs to Z. A comma B belongs to Z. So there is a relation between A and B if and only if A minus B is divisible by Z. So here comes a new definition called divisibility. So what is the divisibility? What is the definition of divisibility on the set of all integers? Divisibility on Z. Okay. Suppose A comma B, we are taking non-zero element, B 2 elements in Z. We say that A is divisible by B, or B divides A if there exists some integer, say n, such that A is equal to B, and we denote it by B divides B slash A, and we read it as B divides A, or A is divisible by. So this is the notation, and we read it as B divides A, or A is divisible by. So this is the definition of divisibility on the set of integers. So definition of divisibility depends on the set that you are going to define. Okay, that you are going to define. Okay. Now let us try to understand whether this relation is an equivalence relation or not. And for that we need to check all these 3 types of relations, namely reflexive, symmetric, and transitive. Okay. For reflexiveness, what we have to show that A is related to A for all A belongs to Z, right? That means we have to show A minus A, that means is equal to 0, is divisible by 5. And this is clear because this can be written as 5 into 0. So from this definition we are getting what? The m should be 0. So that means A minus A is equal to 0 is divisible by 5. That means A is related to A. And since we have taken A, any arbitrary element in Z. So since this is arbitrary, so this will happen for any A belongs to Z. So this implies rho is reflexive. Now come to the symmetricness. For that we have to just wait for a bit. Okay, symmetricness. So for that, suppose A is related to B. We have to show, we need to check whether B row A holds or not, right? So from here we can say A minus B is divisible by 5. That means A minus B can be written as 5 into some K for some K belongs to Z, right? From this definition. So in order to prove that there is a relation, there is a row relation between B and A, we have to show that B minus A can be written as a multiple of 5. So for that you multiply both sides by -1. So we get B minus A is equal to 5 into minus A, right? Since K belongs to Z, minus K is also an integer. And that means B minus A is divisible by 5. That means B rows. And this implies row is symmetric. Okay. Now, suppose for transitiveness, there is a relation between A and B, there is a relation between B and C. For transitiveness, we have to show that there is a relation between A and C. So from this, we get A minus B is equal to 5 into K, so 1. From this, we get B minus C equal to 5 K2, or sum K1, K2 belongs to Z. Okay. So you add them. You will get A minus B plus B minus C 5 K1. This implies A minus C is equal to 5 into K1 plus K2, right? Since K1, K2 are integers, their sum will also be an integer. And this means A minus C is divisible by 5. And that means A row C holds. So row is reflexive, transitive. So row is transitive. And this implies row is an equivalence. Row is an equivalence relation on set. Okay, let us come to another example. Suppose A be the set of all straight lines in the three-dimensional space R3. A be the set of all straight lines in the three-dimensional space R3. We are going to define a relation on that set A. Let us define a relation row on A row B. There is a relation between A and B where A and B are coming from the set A. That means A is a straight line, B is also a straight line. So A is related to B if and only if A lies on the plane of A lies on the plane of B. What is called plane? Plane is a surface in three-dimensional space on which plane is a surface in three-dimensional space on which you take any 2 points on that surface and join them by a straight line. If that straight line lies wholly on that surface, then that surface is called a plane surface. Okay. For example, this is a plane surface. The whiteboard is a plane surface, because if you take any 2 points on that surface and you join them by a straight line, then that straight line lies wholly on this whiteboard. So this is an example of plane surface or plane. Okay. Now let us check whether this relation is reflexive or symmetric or transitive, etc., etc. For reflexiveness, we have to show that A is related to A for all A belongs to A. And this is clear, right? Because A is a straight line. To show that, so any straight line lies on a plane, right? So if this is my straight line A and this is my plane containing the straight line A, so automatically this straight line A also lies on the same plane. So this is trivial for all A belongs to A, because every straight line lies on the plane of that straight line. Every straight line lies on the plane of that straight line. Okay. So this is trivial. So rho is reflexive. Symmetric. For that, suppose A is Z to B. That means what? A lies on the plane of B. On the plane of B. What it says that, suppose this is my plane on which the straight line B lies. On which the straight line B lies. Okay. Okay. Then this is my assumption. To prove the symmetricness, we have to show that B lies on the plane of A. First assumption, what it says that, suppose this is my straight line B and this is my plane containing the straight line B, and this implies on that plane A lies. So this whiteboard is also a plane containing the straight line A. So to prove that there is a relation between B and A, then we have to show that the straight line B lies on the plane A, and this is trivial from this picture, right? So if A rho B holds, then B rho A automatically holds. And this implies rho is symmetric. Now let us check whether this is transitive or not. So for that, we suppose there is a relation between A and B. There is a relation between B and C. If this is transitive, this relation is transitive, then this must hold. A rho C hold. Okay, but this in general does not hold. That we can see. What it says that A lies on the plane of B. Suppose this is the straight line B, right? This is the straight line B that contains in this plane. Okay. First condition says that A lies on this plane. Second condition, this is my A. Second condition says that B lies on the plane of C. Suppose this is this book, plane surface. This is a plane containing the straight line B. this is the plane containing the straight line C, and by this assumption on this plane B lies. That means the plane should be like this. So it is quite obvious from this picture that the straight line A may not lie on this plane C. This is the plane C, this is the plane. Okay. So these two together may not always imply a rho C for this particular example. So this example shows that rho is not transitive. Rho is not transitive. So this is an example where rho is reflexive, symmetric but not transitive. Let us take another example. Suppose our set A is the set of all natural numbers. It starts from 1, 2, 3, 4, 5, so on. So set of all natural numbers. We define a relation rho on N by there is a rho relation between A and B if and only if. This notation stands for if and only if A divides B. So here again comes the concept of divisibility, but divisibility on the set of N, right? Here comes the definition of divisibility on the set of natural numbers. So on the set of natural numbers, naturally these two elements will come from set of all natural numbers. So we don't need to take this assumption. So this not integer here some, so here will be the positive. So N will be the positive integer. So this is a definition of divisibility on the set of all natural numbers. Okay. Now let us try to check all these three relations. First one, reflexive. Whether this relation is reflexive or not. For that, A rho A will hold for all A belongs to A. And this is trivial because every natural number divides itself. From this definition it is clear. A, that means A divides A. We have to prove that for all A belongs to A. And this is trivial because A can be written as A into 1. A can be written as A into 1. So this holds for all A belongs to A. And therefore rho is reflexive. Number 2. Suppose A is related to B. That means A divides B. But this does not mean that B also divides C. You can take a particular case also. For example, suppose A is equal to B is equal to 4. Then it is trivial that A divides B, right? 2 divides 4. But 4 does not divide 2 from this definition. Because we cannot get a positive integer for which 2 can be written as 4 into that number second. And that should be a natural number from this definition. So we cannot get any positive integer k for which 4 into that positive integer will, for the product of these two will get 2. We cannot get such type of k. So B does not divide A always. So this relation is not symmetric. This relation is not symmetric. Okay. Next, transitive. transitiveness is clear. Suppose A is related to B and B is related to C. If it is transitive, then we have to show that A is related to C. That means we have to prove A is related to C. That means from this definition, A divides C. We have to show that. From this, we can get A divides B. From this, we can get B divides C. From this, we can get, from this definition, B is equal to some A K1, where K1 is a positive integer. From this, we can get C is equal to some B K2, right? Where K1, K2 are some positive integers or natural numbers. Okay, now put the value of B here, A K1, K2. So C is equal to A into K1, K2. Since K1, K2 are natural numbers, their product will also be. Whenever we assume these two relations, but these two or these two conditions, we can prove that this relation, or there is a relation with A and C. So this is a rho is transitive. Okay, so this relation is reflexive, transitive, but not symmetric. Okay, let us take one more example. After that, we shall move on this point. Okay. Number 4. Suppose our A is set up all integers. And on Z, we are going to define a relation rho with this way. We define a relation rho on Z by A is related to B if and only if their product strictly greater than 0. If and only if their product is strictly greater than 0. Okay. Now let us check all these three types of relation holds or not. For reflexiveness, we have to show that A into A is related to B. Sorry, A is related to A for all A belongs to B, right? We have to show that. But this does not happen. For that, we need to show that A into A, that means A square always greater than 0 for all A belongs to B from this definition. But this does not happen for all A belongs to Z. For example, if you take A is equal to 0, then 0 into 0 will be equal to 0. That is not greater than 0. So this is not a reflexive relation because there is an element here 0 such that 0 into 0 is equal to 0, which is not strictly greater than 0. So rho is not reflexive. Number 2. Symmetric. So for that, suppose A rho B holds. That means from this definition, product of A and B is strictly greater than 0. Now product of AB greater than 0 means product of BA is also greater than 0. Since the product of multiplication is commutative on the set of all integers. Okay. So this implies B rho A holds. So B rho A also holds. So this is symmetric. Rho is symmetric. Now for transitiveness. Suppose A rho B, B rho C hold. For transitiveness, you have to show that A rho C holds. So from here, we can say A, B plus t greater than 0. From here, B into C is greater than 0. Okay. Now take the product. A, B into B, C is greater than 0. Now AC into B is square greater than 0. Now B cannot be equal to 0 from this observation. Because if B is equal to 0, then A dot 0 equal 0. A dot 0 equal to 0. But here is still greater than 0. So B cannot be 0 element. So if B is, since B is non-zero, so B is still greater than 0. And that means A is equal to 0 since B square is equal to 0. That means A is related to C. So this is an example where the relation is not reflexive but symmetric as well as transitive. So let's come to the last point of this video lecture. Fallacy. Okay. Suppose rho is a relation. Rho is, say, symmetric. And transitive on defined on the set A. Also, suppose that A is equal to B, that A comma B belongs to B, right? Okay. Now A rho B implies B rho A, since rho is symmetric. Okay. Now A rho B and B rho A together implies A rho A, since rho is transitive. Here we are seeing that. So we are getting A rho A holds. So from there, can we say that rho is an equivalence relation? For rho to be an equivalence relation, we have to prove that rho is also a reflexive relation, because we have already assumed symmetricness and transitiveness. So for equivalence relation, rho must be also a reflexive relation. So from our discussion, can you say that rho is reflexive? From our discussion, it may seems that rho is also a reflexive relation, because this relation holds. But this is not true. This is not always true. Why? The point is relation rho is reflexive if A rho A holds for all A belongs to A. For all. This should happen for all A belongs to A. This is point number 1. This is and the point number 2 is here we are getting this relation on the assumption that well, take this on the assumption that this there is a relation, row relation between A with itself only if there is a relation between A and B. That means for the element A, if we get another element on that set A such that there is a relation between A and B, then only we can get this portion. Okay, so this portion depends not only on the symmetricness and transitiveness, but also depends on that assumption. What the assumption says is that for a particular value A, if there is a element B in A such that there is a relation between A and B, then only we can get this relation. Okay, but this may not always happen in general. For example, in the previous example, we have shown that we have taken A is equal to Z, and the row we have defined in this way. There is a relation between A and B. We can only A product of A and B is equal to 0. And particular for this relation, if we take A is equal to 0, then we cannot get any element on Z, any element B belongs to Z, such that 0 into B will be the product of 0 and B will be greater than 0. So this, from this we cannot say that row is reflexive. So row is reflexive only when this will happen for all A belongs to A. But it may seem, but this does not hold in general. For example, we have seen that in the previous example, we have seen that row is not reflexive, but it was symmetric as well as transitive. So reflexiveness, symmetricness, transitiveness, all are three independent definitions. One cannot imply other. That's why we have defined an equivalence relation only when a relation is an equivalence relation only when row is reflexive, symmetric as well as transitive. Okay, so let's stop here. I think what I have taught you have understood.